Brandon, I'd like to welcome you to our humble Israel Web3 community. It's a relatively new community. A lot of developers are coming from the Web2 world with relatively little experience in Web3. Some of them, though, are very, very knowledgeable. I want to introduce Brandon. I got to meet Brandon face-to-face when he was here in Israel. What was it, a month or a couple of months ago?
About 1 month ago.
Yeah, that feels like a year ago. Like everything is moving so fast in this industry. As part of a tour that he was doing of Israel, and I got to learn a lot about zero knowledge and SnarkyJS and the Mina Protocol, which I had no idea about before. So I thought it would be an amazing experience to get Brandon to explain to us about zero knowledge proofs, basically how Mina Protocol works, how to use it as a developer, and basically get us up to speed and maybe introduce us to this world. I think a lot of developers are coming from the kind of standard Solidity, Ethereum, EVM world. And I think most of the people that I've seen so far don't have a lot of knowledge about zero knowledge proofs and how that can help. So we look forward to hearing from you, and take it away. I'm gonna mute my screen so that we can see you.
Okay, cool. Thank you. Yeah, so I'm Brandon. I work at O1 Labs. That's that logo in the corner. We are the what is the term? We help incubate the Mina protocol. So I've been working on Mina, or the pieces that eventually became Mina, for about 5 years. So I know a bunch of details and can answer a lot of questions. And recently I've been personally focused on SnarkyJS and building out our smart contract system. So that's what we're going to talk about today. Cool. So I want to talk about Mina and zkApps. That's like our spin on dapps. SnarkyJS, which is the programming language or library, depending on how you look at it, for writing these smart contracts. Then we're going to go over a hello world. And maybe we'll have time to go into like a bigger example too, depending on how questions go. And we'll talk through questions. So Mina, okay. Before I talk about Mina and before I talk about zkApps, I'm just going to talk about other protocols. So other protocols, other layer ones have blockchains, and those blockchains grow. And all nodes in the network, in a typical cryptocurrency protocol like Ethereum or Bitcoin, they store every block. And as long as they're full nodes with full security in a fully decentralized network, they're going to store every single block. And as the network grows, as more transactions happen, as the network moves forward, the blockchain grows. So Bitcoin is over 400 gigabytes. Ethereum, like full Ethereum history, is much bigger than that. I don't even know what it is these days. More than 700 gigabytes after doing some pruning. And Mina, in contrast, is 22 kilobytes. This is precisely defined if you go to the Mina Protocol website. And there's a sentence about this, and then there's like a link to look at a detailed blog post. So I don't want to go into too much detail about sort of how we calculated 22 kilobytes, but just to give you a sense. So in Mina, like just like a typical cryptocurrency protocol, like there exists a blockchain, but in Mina, nodes in the network don't store the blockchain. They store a zero knowledge proof that stands in for the blockchain, and the zero knowledge proof says there exists a valid blockchain. But I don't know what it is, such that like the current state of the world is this. And the way that the network moves forward, the way that new blocks get added to the blockchain, is a new zero knowledge proof is created that like subsumes the prior zero knowledge proof. And then it's kind of like that animation there. So like a new block comes in, and we take another proof, and because of the nuances and interesting cryptography underneath, which I'm sure in this group, a lot of you know a lot of details about, but it works. So we call this a succinct blockchain, a blockchain that's backed by like a single zero knowledge proof. You can also think of it like a roll up of but it's a roll up sort of on the L1 layer. But maybe that helps some people who are familiar with that term. So and then the recursive snarks, the snark system that we have that we're about to launch on our hard fork, it's called Kimchi. So Kimchi is a proof system that is setupless. So there's no trusted setup. If you're familiar with Zcash, there's a ceremony for the original Zcash, and you have to have there's some trust assumptions there. There's none of that. It's efficient. It's very, very quick to verify proofs. And the interesting thing about Kimchi is it's extensible. And what that means is the thing that we're proving can change dynamically. And we're going to take advantage of that to write smart contracts. So and I should say Mina is a protocol that's on mainnet. It's been on mainnet for over a year. We have a succinct blockchain. It's still 22 kilobytes by the semantics that are defined on that website, and it will continue to be. But there's a version of Mina that lives on.
Okay, I see you. Tom is asking a question. You don't want to just open your webcam and ask. Okay. You mentioned similarity to Zcash. Is Mina also taking privacy into account, or are you focused on blockchain size?
Yeah, so privacy is not present on the L1 by default, but you can implement it as a zkApp. So yeah, we use the same underlying zk-snark technology, or at least similar. But rather than using the zero knowledge part to hide information, we're using it to work around having to store it. If that makes sense. So yeah, we're focused on data privacy rather than, I guess for the purposes of consensus, focusing on sort of hiding data, compressing data rather than making it private. I don't know if that was helpful.
Okay, Tom, you have to go like this if it's good, or if you have more questions.
Yeah, no, it's great. It's great. Actually, if I can have another question, then so you mentioned that you have a trustless setup.
Yes.
And Zcash just upgraded their network to use Halo. Are you familiar with that?
Yes, I am. Yes. So if you want more details of the Mina proof system, I'll throw out some words that some of you in the room might be familiar with while my browser's reloading. So Mina's upcoming proof system, at least, and because that's the one where I've remembered all of the specific buzzwords here. So it's based on Halo 2, so similar to the Halo system of Zcash. We use the pasta curves, which is the same curves that the new Zcash stuff is using as well. It's a Plonk-based proof system, so there's lookup tables to speed some stuff up, and then I guess if you want to read more about our proof system, Pickles is the version that's on mainnet, and then Kimchi is this version that is about to be released. And everything in our proof system toolbox we name after pickled vegetables. That's the theme. So okay, I think we're good again, hopefully. We fix this. This is the most technical difficulty I've ever had this year. So sorry. Okay, get my head in the game. All right. So let me go back to where we were here. Okay. So anyway, I think we get the idea. There's a cool crypto system underneath Mina, and we have a fixed size blockchain. So let's change our headspace to dapps. So if we think about Ethereum dapps, and this is typical of any of them really, any EVM based ones, or even Solana, etc. In in the application, when you go and visit the application as a user, and you want to do something to the chain, you send a transaction, and in that transaction payload includes some instructions. So, and those instructions get sent to the network, and then every node on the network, in the case of Ethereum, runs every single instruction in that transaction payload. And moreover, even as new nodes join the Ethereum network, if they're catching up, they're re-executing every instruction that has ever been sent. So there's a couple of things going on here. One, it's not so scalable, or it's not very efficient, I should say, because what you're paying for is every node in the network to run every instruction. And we can't really do things with privacy here, because the data that you're computing on gets sent to people who you don't trust. In contrast, for zkApps on Mina, execution happens on the user's machine, off-chain. And then what we create when we execute the smart contract is a zero-knowledge proof, plus some, the changes we want to make to the state of the world. And just the proof and those changes get sent to the network. And the nodes in the network, they verify the proof and they apply the changes. But they don't run the computation, and they don't know about any private information that you used in the process of running your computation. So it's pretty cool. So basically what we talked about, right? There's succinctness at the blockchain level. So we get scalability in Mina through there. And then with smart contracts, we have privacy and this kind of efficiency that comes with off-chain execution because the smart contracts execute before they get to the network. So it's pretty cool. And I guess one thing I should note, on EVM chains and most chains, you pay gas proportional to the computation size that you're executing on the network. In Mina, you pay gas proportional to the number of proofs that you send to the network. So you can do something that is a very simple computation or a very complex computation. In the end, you get one proof and you pay for the one proof. So there's a predictable pricing model as well. So just to kind of get ourselves in the headspace of what you can do with this thing. Oh shoot, I should have refreshed. Anyway, I had shekels here, but we're gonna have to survive with US dollars because I forgot to refresh the slide.
Change to USDC instead.
Yeah, USDC. So, well, actually, in this case, it's US dollars, fiat. So let's say that I want to prove on chain that I have more than 5,000 US dollars in my real world bank account. I'll just pick an American bank, Chase. I don't know. So with zkApps and with a couple other pieces of infrastructure that the Mina ecosystem is building, that's not quite ready yet, but getting there. We can pull data from Web 2, so like your bank, and use like bootstrap off of the TLS signature, that like green padlock that you see when you visit a secure website in your browser. Pull in information and create a proof that my bank attests to the fact that I have some amount of funds that I'm keeping private that is greater than $5,000. And we can bring that on chain with zkApps. And then that proof, when it settles on chain, can be bridged to other chains like Ethereum or Avalanche or others when all the bridging infrastructure is in place. So that was just kind of a teaser to get your head in the space of possibilities here with this privacy. Cool. Okay, so I'm going to switch gears to just zkApps at the architecture level. Okay, so if we think about a zkApp, there's two pieces. There's a user interface and a smart contract. So it's similar to a dApp where there's a user interface and smart contract. I'm going to just focus on the smart contract part. The UI for the rest of this presentation. The UI though is like a typical web UI application. So you can use React, you can use Vue, Svelte. I don't know what's hip these days, but Rails, anything. So, but the smart contract part, that's the new thing, I would say. So let's talk about that. So SnarkyJS is our toolkit that you use to write smart contracts. When you compile a smart contract, you get two build artifacts. So this is different than like a typical, something that's typical, I guess. So the two artifacts here, it's a prover function and a verification key. So the prover function is the thing that you import into your React application, into your web app. And that's just a function, an asynchronous function that you call, it returns a promise, that you call from your web application. So this is what you call when you want to, do an action on your application. And this creates a proof, which can be sent to the chain. The verification key is what's needed to verify proofs. And because we're going to use Mina's blockchain to verify the proofs, we have to send the verification key to the chain. So when you're deploying a smart contract, you deploy the verification key. So the verification key goes to the chain. And when you do this, you create a zkApp account in the ledger. So it's like an account that has a balance and all these things that a typical account does on Mina or on any blockchain. And it has a bunch of extra fields that are useful for zkApps. When a user is interacting with a smart contract, or a zkApp, and they press the submit button, we execute the prover function, create a proof, create the state updates. This then gets packaged up in a transaction and can be handed off to a wallet like MetaMask, or in Mina, there's a browser wallet called Oro. And then that transaction, if the proof is valid and preconditions hold, which I'll talk about, which I'll get to in the Hello World example, then the transaction will be accepted and the state updates will be applied, and you can be assured that the proof is valid. If the proof is not valid, or there's precondition violations, like for example, if you depended on a certain time or a certain block height for your execution to be valid, then the network will accept the transaction, take the transaction fees, but not apply the state updates. So the actual state update part will fail. Okay, one more slide on this, like sort of abstract nonsense, and then we'll get into code. Okay, so methods in zkApps, similar to Solidity, these are the entry points of your smart contract that maybe different buttons in your UI invoke. They have inputs and outputs. So the inputs can be partitioned into sort of two sets. There's the private inputs and the public inputs. So the method's arguments, those are private. So as long as you don't expose them in some way, like storing them in a public area, then they'll remain private. The public inputs are a state that's in the smart contract, in the smart contract account on chain, and state about the world, which is on chain. So the time, the height, maybe someone has brought Web2 data on chain, but anything that's on chain. And then all of that's public. Then the method executes, and the outputs are, in addition to the proof, they're state updates about the smart contract state. Maybe we're going to store some piece of data, and then maybe we're going to change the world somehow. Like we're going to move assets around between two accounts. So specifically, like these updates come with associated preconditions that must hold for the updates to be applied. And like I was saying, like you might have your smart contract only work if it's executed after a certain time or before a certain time. Cool. Okay, so let's see code. SnarkyJS. It's in TypeScript. You use your normal TypeScript tools. You can also use JavaScript, but we've spent more time on the TypeScript interface. NPM works, Prettier works, ESLint. Everything is typical. There's a I don't know what you call it, a command line tool called zk. So you can install that. The zk tool was not taken by any popular project, which is great. So it is now claimed. That's how you install it. And this tool will help you like generate a project template, has examples, and it helps you deploy the smart contracts to the network, to testnet, to mainnet, et cetera. After we hard fork the mainnet, that will work. Cool. So let's go deeper. Let's see some code. Just to highlight, it runs in the browser because it's just TypeScript, it's just JavaScript. You can also run in Node.js, so you can do a server-side things, and as I said, use existing tools. I'm harping on this because if any of you have played with most Web3 tools, but Solidity feels a little bit like JavaScript, at least. If you've played with any zk programming tools, you may, if you're like me, wish that it was something that was more familiar looking. So a like big design decision that we made is to build on top of an existing popular programming language that already has good tooling, because that's what people already know. You already have to learn about zero knowledge proofs, so that's maybe enough. You don't have to learn a new programming language. Okay, so the base unit of data in zk programming is typically, and is for this proof system, is field elements. So field element is in Mina's proof system. It's a number that is it's actually a big prime number is the maximum, but it's really close to like a uint 256. So it's very close to that. So when you're programming in a typical like Web2 or backend environment, you might use like JavaScript's weird, but if you're programming in a typical programming language, you'll use like a 32-bit integer or a 64-bit integer because that's what your CPU understands. The CPU for zero knowledge proofs understands 256-bit or almost 256-bit numbers as this primitive. So and this is the field type with a capital F in SnarkyJS. So just like a bunch of random basic things. SnarkyJS comes with field, which is like int, bool. There are the typical like uint32, uint64, signed integers, etc. But those are like built on top of field. Everything's built on top of field. There's other cryptographic primitives that might be useful. And functions in SnarkyJS are TypeScript functions. So that's that first code example there. It's just a function. So this is a function that takes a field element, it adds 1 to it, and then it multiplies it by 2. And we return a field element. The data is typical TypeScript data. So classes, JavaScript objects, arrays, just typical TypeScript, JavaScript data. Just a nuance here, like field elements are not JavaScript numbers. So so like that second example there, like integer or numeric literals in JavaScript need to be wrapped in a field package. But we have syntactic sugar like when it can be inferred. So in the case of that function, for example, the syntactic sugar, makes it so you don't have to say new field of 1 when you're adding. So, okay. Hello world. Let's do it. All right. So we're going to write a smart contract with a single state variable called x. And we're going to have a single method, a single entry point called update that's going to let us replace x with its square. And we're only going to be allowed to do this if we control a secret private key that's like an administrator private key. Okay. So for example, we can deploy the contract, let's say with a start state of 3. And if we supply the admin key and 9, then this proof and the updates will be accepted on chain. And now X will have 9 as its value. And we can do this again with 81, and this is valid. Now, if someone gives 9 and then someone tries to update without passing 81, well, the proof will just not be generated if you're using the proper tools. And if you try and break the system and you send an arbitrary binary payload, then the network will not accept your proof because verification will fail. So just the nature of how ZK snarks work, you can only verify proofs that were created properly. So this is exactly what we want. Okay. All right. Now we can finally look at code. So to make a zkApp smart contract, you extend smart contract. Simple. For state, on-chain state, you make a class level field, and you use a decorator. So decorators in TypeScript aren't very widely used, but they're interesting because they let us abstract away a bunch of complicated nonsense under the hood. So unfortunately, you have to repeat yourself a couple times here. It's like reminiscent of Java programming, if anyone is familiar with that. But trust me, it's much nicer this way than the alternative. So this is declaring X as a state of type field, and you can build on-chain state out of anything that you can build out of field elements. And if we have time, I'll show a more advanced example of this. Cool. Okay. So now we're going to say what happens when we deploy the smart contract. Okay. So we override a deploy method on the class and call super. And then the first thing we do is we say this.x, so we get a handle to that state variable, and then we set it to 3. And the mental model you should have here is x does not actually equal 3 in the universe at this moment when this code is executing, because the code's executing off-chain, and x will equal 3 on-chain. So what this.x.set3 does is it adds to the list of updates that get sent to the chain, change x's value to 3. Okay. The second thing we do is we're going to store the admin public key in an interesting way. We can store it in on-chain state, but I just wanted to show like another feature of zkApps. We're going to, well, it turns out accounts on Mina, they have this delegate field. It's used as part of staking. We're not going to actually use the delegate field for its purpose in our smart contract. So we can just use it as some extra state. And it turns out it's exactly the shape of a public key. So we want to store a public key. So let's just store it in the delegate field. And that's what this invocation does. It's maybe something that we'll have to like clean the API a little bit, but this is how you do it right now. Okay, so now the admin key is set up. We don't want to reveal the private key, right? So this is just the public key, and X is 3. Now we're going to implement the actual method, the entry point. So to write an on-chain smart contract method or an entry point, I guess, you write a method that has the @method decorator in front of it. Okay. So each of these can have their own logic, similar to Solidity methods, if you're familiar with that. But just think of it like a function or a method in TypeScript. And arguments to the method, those are private. So arguments are private, and state is public. That is the exception being if we like obfuscate the thing that we want to store before we store it publicly, then well, it's still private. Or if we have something that comes in as private, but then we store it publicly, then now it's public. So in this case, the first argument here, squared, this is the next state in the execution here. So X starts at 3. Let's say it's 9. And then the first thing we do is we get X's value from universe, the current state. And then we assert that the square of x dot square, is equals to the squared input, the argument there. Now this assert equals, it's not a debug function. It's a function that does something. It introduces a constraint to your zero knowledge proof. So we're saying only accept inputs, this private input, if it can satisfy the constraint that x squared equals this value. And okay, so we do that, and then we set x to that new value. Okay, but we only want to do this when the admin private key corresponds to that public key that we set when we deployed the contract. So, sorry. So let's do that. So what we do here is private keys have a method on them to public key, which returns a public key, and it also sets up a bunch of constraints in the zero knowledge proof to make sure that the transformation between private key and public key is correct. And then we can reach into the account of this smart contract by doing this.account, and then look at the delegate field and assert that it equals the admin public key. So you can reach into this specific zkApp account with this.account, and you can reach into the network state with this.network. And it's similar. You can say this.network dot block height assert equals 10, or assert greater than 10, something like that. Perfect. So that's it. That's it, actually. So when we actually execute this method, what we're doing, what a user's like JavaScript runtime is doing, is it's we're executing the code, and then we create a proof that says we ran the code in this method with some private arguments, and I don't know what it was, but it was something. And the results of that execution are that we want to update the x to be 9 specifically, if the following preconditions hold: that x was 3 in the beginning, that the delegate public key is equal to the admin public key, and the admin public key is like associated with the admin private key, such that the transformation is valid. And if all those preconditions hold, when this proof is verified on chain, then the state update will be applied, and the contract execution will be successful. So, in summary, state variable, deploy method. Okay. So I can pause for questions, but I would like to show a more interesting example with a lot more code for this room. So maybe we'll do like 5 minutes of questions, and then I'll jump to that.
Yeah, so there are a few questions in the chat, some of them by me, some of them by others. Boris asked, or Boris, do you just want to ask, or do you want me to read it?
Yeah, for sure, no problem. Basically, my question is that zk rollups in the Ethereum ecosystem still need like a data availability layer to pose the transactions. And because you will like keeping the state very small, you probably did some workaround around it. So if you could describe the differences.
Yeah. So the I guess for Mina's consensus layer, well, there's a couple layers to this question. I'll say one thing that I just think is interesting that I won't go into too much detail in, unless people want me to, but Mina, like the L1 Mina, can sort of be an L2 for any chain that has a bridge to it, because the Mina bridge essentially, like smart contracts on Ethereum or any chain, essentially run full nodes of Mina because the blockchain is so small. So there's a way to answer that question if you think of the rollups in that context, but I'm going to answer it in the L1 context, which is that I was simplifying something that actually is more complex under the hood. But I guess the nuances of Mina's consensus mechanism are very interesting, and we have security proofs and assumptions and things in the white paper. So I guess I recommend you take a look at that to kind of get your head around how that specific issue is solved. So that's actually probably there's the Mina technical white paper, and it's on archive, and it's linked on the Mina Protocol website.
So in your examples, you were showing, so if I understand correctly, when you write code in that TypeScript, that hello world, if you will,
yes,
it's basically a kind of a syntactic sugar that gets translated into a zk proof. So it just looks like JavaScript, but it's not actually running JavaScript. And what I've seen so far is that you wrote the asserts are basically kind of like requires, but at the proof level. So do the asserts or do they only work on mathematical stuff, or what happens if you write logic like loops and stuff like that? How does that work as part of a proof? I mean, I don't understand how proofs work, I guess. So I'm asking a very
great
new question here.
I heard like 7 questions in one there. So I'll try and answer all of them, but tell me if I missed anything. So the first thing is one of your assumptions is actually different from what you're assuming. Assuming I understood what you were saying, which is so SnarkyJS. Maybe I should share my screen again. I will. Okay. So actually, you are executing TypeScript. So this is TypeScript. It runs in V8, like in your browser's JavaScript runtime, or in Node.js. And what we create in the end. So you're also right that we're constructing a zero knowledge proof object. Or rather, we're constructing instructions to create a zero knowledge proof object. So the JavaScript runtime, like all these methods here, when we call an assert, when we set, when we do other sorts of things, you can think of it as like appending. I don't know. We're constructing a small data structure. That gets fed into a WebAssembly like Rust proof creator thing, but that data structure is like metaphorically like assembly language. So you don't want to write assembly language. You want to write something that's a bit higher level. And I guess in some ways, like I mean, it's hard to say like what is a compiler and what's not a compiler. But this is just TypeScript.
Yeah. So I guess what you're saying is that as you're so it does run in the browser and it generates a data structure. So you're translating it into a declarative set of assumptions that are then static in nature. They don't actually execute. They get fed into into a machine that converts the static specifications of you can think of it like a series of assertions, essentially like a series of constraints that gets fed into this cryptography black box function that outputs a proof object, like some binary data that you can serialize and send around. But then does that mean that does it work on dynamic information? So example, if you have an unknown list amount in a list and you loop over it and you generate assumptions to a proof, what happens if you get 4 but you only generate 3 assert equals because originally you only got 3? Or does that make or you have to assert
that does make sense
amount?
Yes. So I should have had an example of this in the slides, but I will show it in the code that I show in a moment. Yes, every execution must be static. So in the sense that if statements are a bug, unless like you're doing something really, really fancy, typically if you're using if statement, you're doing something wrong. But you can use an if combinator, like an if function that has a condition, a then branch, and an else branch, and that will morally do the same thing. Similarly, if you want to loop and if in your loop you're just sort of setting assertions, but the loop's bounds are static, then like that will work because you're setting the same number of assertions. But if you are doing something that's more dynamic, then you can't use a simple loop. But there is a more fancy way to make it work. And I'll say like for those in the room who are familiar with proof systems, the Planck part of Kimchi it sort of gives us the power of arbitrary jumps in the proof language. And if you can do arbitrary jumps, then you can do loops and you can do array indexing and things like that. That I'm going to say that is out of scope for this conversation. Exactly how that works. It's really intense.
It's like a go-to statement. That's what it feels like. But you're basically writing purely functional code in a way that's basically that's very cool.
Yeah. And there's an alternate design for this framework that is very purely functional in how it feels when you write it. And our current design, we've purposefully like hidden some of that to make it more approachable for people. So using classes, using assertions as statements that sort of mutate the world's consciousness. But we're going to be experimenting with a more functional API as well, and we'll see what the community feels is easier to work with.
Anybody else have any other questions other than me hijacking conversations left and right? Okay, I guess we should go on.
All right, so I'm going to share. Let's see if this works. I'm going to share a VS Code window. I'm going to attempt to share a VS Code window. Okay, I think it works. Yeah.
Yep.
Is this a good Zoom level?
Wonderful.
All right. Perfect. Okay. So this is a Sudoku example. So the idea here is, and there's a UI for this somewhere, but I don't have it. I don't have it checked out. But the idea is one person deploys a Sudoku problem to the chain with so I guess I should show Sudoku. All right, so Sudoku is this game where there's a bunch of numbers and holes. And I wish I shared my Chrome window first. So bear with me. But anyway, there's a bunch of numbers and there's holes, and it's a puzzle. And to solve the puzzle, and it's a 3 by 3 by 3 matrix, the puzzle. And in order to solve it, you must fill in all the holes. And the rules are that you can only use numbers 0, or it's 1, right? 1 through 9 once in every 3 by 3 matrix dimension, I guess, in every like cube. Hopefully, you know what? I'm just going to show a picture of this because this example is going to be way too confusing if you don't know what Sudoku is.
I think everybody knows what Sudoku is. I think it's very common here.
All right.
Yeah.
Then
you can always show a picture.
You're right. It's just more likely to mess up to have more technical difficulty. So, all right. I hope you all know this. Okay. So we're going to write a smart contract that when we deploy it, we're going to deploy a specific problem statement of a Sudoku question. And then the method, the entry point to the smart contract for users is going to be a solution to Sudoku. And we're going to hide with zero knowledge the actual details of the solution. And we're just going to reveal if that solution was valid or not. Okay. I'm going to just pause to make sure there's not a question about this, because there's going to be a lot of code and I don't want to confuse people. Okay. All right. I'm going. So, so there's imports. This is just from the SnarkyJS library. There's this annoying thing about the way that our backend works, that you have to await this this promise before you can do anything, before you can set up different smart contracts. So we'll try and work on getting rid of that dependency. But right now, there's like web workers and WebAssembly, and there's like WebAssembly from Rust and WebAssembly from OCaml, and it's like a crazy backend. So you just put that at the top. And now I'm going to show an example of sort of defining a composite data structure out of field elements. Okay, so the Sudoku board, we're going to store it as a 2x2 matrix instead. So rather than a 3x3x3, but here there's this matrix prop attribute. We give it a type and the length and height and width, and then you get an array of field elements that behaves like a primitive. Okay.
Can I ask what is a circuit value?
Yes. So a circuit value is a poor name, and I would like, and probably the name is going to be different the next time you look at this library, because I don't like using circuit anymore. But circuit value is something that the proof system understands in some way. So, for example, you can store circuit values as state on chain, and you can do other things with the proof system when it's a circuit value. And essentially, like the circuit value class doesn't really help to look at that. But essentially, it's defining something that's built out of field elements. So this is like syntactic sugar, but you can implement this with like 2 field elements, and then like from field elements. And this returns Sudoku. This returns field elements. Yeah. So if you implement these 2 functions and like a couple other tiny things, then you implement circuit value, and then you can do proof system things. But this decorator does that for you. So yeah, I don't know a good name. Well, this name will probably change. I'll just say so that people understand. Some people refer to like setting up the details of the proof as constructing a circuit, because they're like one potential implementation detail of the proof system is that it's backed by an arithmetic circuit. It's this like mathematical structure. I don't like using this term because there are other representations of setting up the structure of a proof, and SnarkyJS is like agnostic to those backends. So this is kind of like an abstraction leak using this term here. Anyway, okay. So the smart contract, we extend smart contract, right? We're going to have 2 state variables, the hash of the Sudoku, and a Boolean that says if this particular Sudoku is solved. Okay. So I guess one other way to view this is like it's a game, and the first person who solves it wins, and no one else will be able to solve it after them. But you can tweak this in different ways and change the semantics of winning. So sorry, this should be deploy. Or did we, someone updated this and I didn't code review it. Okay, I guess we changed deploy to, oh, no. Sorry, this is deploying, this is built in a way that you deploy it and you initialize it afterwards. Sorry, I haven't looked at this since someone has edited it. Okay, so deploy is not overridden. So the deploy is the default, and we're going to initialize Sudoku with one of the smart contract entry points. Okay, so we take a Sudoku instance that has holes in it, right? It's a matrix of field elements, and then we're storing on chain the hash of this Sudoku board. Okay, and we're going to use this hash in our smart contract later, and then we're going to store solved to false. All right, cool. So the submit solution. All right, so we give it the problem statement board and the solution board. Okay, so this one has holes in it, and this one has no holes in it. If you're behaving as an honest actor, so we have to make sure our logic checks that. Okay, so we're going to define some helper functions. I won't go through these in too much detail because it's just maybe it's something you can trace in your free time. But this creates 0 through 9 in an array, and then this creates 1 through this is 0 through 8, and this is 1 through 9. So we're adding 1 to the indices and then wrapping it in field. And then this helper function here, it asserts that this particular 9-element field array has 1, 2, 3, 4, 5, 6, 7, 8, and 9 in some particular permutation. So let's see. I don't want to go through all the details here, but the important thing is, like, this is an example of something that we can't easily write in a for loop, and we have to use like map and reduce, or with a for loop you'd have to use a lot of mutation, because we're trying to construct like this sort of compound Boolean statement, and then we only want to make one assertion at the end. So we could like we could do this with a lot of different Boolean assertions, but that's actually a lot less efficient than like taking all of our Booleans, anding them and oring them, and then asserting that the result is true. So I don't want to go through the details here because it's not going to illustrate much about SnarkyJS. So cool. So checking all the rows, we can call our helper on the rows. We can call our helper on the columns. And then this is like the Z dimension. But because we've implemented it as a 9 by 9, the math here is a little bit, the indices math is a little frustrating. So so this makes sure that like these 3 sections here make sure that all of those areas have 1 through 9 in them. Okay. And then we want to check that like we actually solved the problem that we started with. So so to do that, we for each of the cells, we want to check that either it was 0, like it was empty, or it had the same value as the solution has. And we're going to take that expression and we're going to assert that that's true, this Boolean expression. Okay, finally, we want to make sure that this Sudoku that you're solving is the one that we actually set in the state. So we have to get it from the state, and then we check that the hash of this Sudoku that we're using again in our contract execution is equal to the hash of the thing that we stored on the chain. And if we do all those things, then and you believe that we actually checked all the constraints, that's an important thing when you're writing a zero knowledge proof smart contract. You want to make sure that you've asserted all the things that need to be asserted. Then we can set is solved to true, and we're done. And then I can go over testing and all these things in a moment if people want to see that. But yes, I'll pause.
Anybody have any questions other than myself? Fine, I'll ask it since everybody's very shy today. It's very, very Israeli of everybody. So I just want to make sure everything you just wrote here, and it gets translated into basically a static object, if you will, that gets, for lack of other words, fed to a proof that is then checked basically on like a functional piece of code. Is that correct? When we execute this, we're constructing our data structure. And at the end of the function call, we have this sort of data structure that gets fed to the proof system black box. And that function turns this like static representation of all these assertions about how the world should look into a proof object. And that proof object we can call in a version of SnarkyJS that's going to be released in like a week or two. You can actually get a handle to this proof object in SnarkyJS, and you can call verify on it in SnarkyJS and verify it locally. But in the current release version, you can verify it by the chain. So you have a proof object, you can then send it to the chain, and the chain will verify it. Does that help? Yeah, it's very helpful to me. So we're at the hour mark. So I want to make sure, first of all, that you have a few more minutes maybe to go over. If you got to go, you got to go. But if you still have a few minutes, I would love personally, and maybe other people too. First of all, everybody, if you have questions, now is the time to either unmute or write in the chat, and I'll read them out loud if you're too shy. But if you do have a few minutes, I would love to see, what do you do after you write this? How do you, when you run the command line, what do you do with the outputs? Basically, maybe even like a diagram, or like, how do I actually, what do I do with this?
Okay, so the first thing that you want to do is you should test it, because maybe we like did something wrong, right? So there's a handy way to create a local instance of Mina. And this is like, we took a bunch of Mina's source code and compiled it to JavaScript. So this is Mina. Like, this is the same logic that Mina will execute on chain, but it's running locally in your browser in Node.js. And then there's a couple helper test things on it. So one thing is you can get handles to test accounts that have a bunch of, look, it says right there, they have 3 trillion units of, or something, I don't know, some large amount of Mina, nano Mina is like the tiniest unit. And then we can deploy the smart contract to our test Mina instance. So the API for this is shown here. I won't go into the details, but and you can send transactions. We can submit a solution to the chain. So I guess I'll show this. So like you start a transaction, and then you get a callback, and anything in here gets sent as part of the transaction. And so like what we want to do is we want to call the submit solution method of the zkApp. And what do we give it? We give it the problem and the solution. And then we have to sign the transaction, and then we can send it. And if it succeeds, then we return true. Yeah. So let's pause. So if we have these functions here, you can also imagine like writing these in a way that they interact with the browser wallet, and they actually go to a real chain running somewhere. But this is just a local implementation. Now we can export these functions. And we can export these functions and then import them from a React application. And then on click, on a button press, for example, or in a jest test, for those that are familiar with JavaScript. In a test, we can write a test that calls deploy or calls submit solution, and then assert things in test land or connect it to a user interface. Does that help get the picture?
Yeah, so you get so basically when you're writing this, you're basically exporting an NPM package. You're creating your own NPM package.
Yes. But, yeah, sorry, I should have said that. Yes. And then you can import it into a user interface and just use it.
Okay, so where's the other part? So I have this front end part that I use. Mm-hmm. What do I do with the other part?
The other part. I guess, so the deploy, typically you'll do that from the CLI. So let me open the terminal here. Move my Zoom thing. Okay, so there's the zk command. If we're deploying to the chain, well, we say zk deploy, Sudoku, what did we call this? So the name of the class, Sudoku zkApp. And then I need to configure a couple things, but if we had like 50 more minutes, I would actually do it. But
we're kind of out of time, and I don't want to take any more of your time. But
is that helpful, or is there any sort of empty holes in how everything connects together? I think that's really important to end on.
So for me, there's one extra piece of information missing, which is, okay, I understand the front end part of my own application, but then there is the Mina blockchain running somewhere, right? Yes. And so how do I get the stuff that I just wrote to run on the Mina blockchain?
Yes. So you wait for one more week. Or you have to like dig into the guts of the library because there's not a super clean API exported by the wallet yet. But imagine, so in like Web3, there's a web3.js, which is something that the MetaMask inserts into your window. So there's Mina web3.js that gets injected into your window, and there's a function on there that's like send a transaction to the wallet, and then the wallet will pop up and do its thing, and then send the transaction. And then you can also get the state from the chain. Mina's implementation, like the Mina node itself, runs a GraphQL server. So you can directly connect to a Mina node and just use GraphQL in your front end, or you can connect through like a public service proxy. So yeah, it's all designed to be like super easy and familiar. I mean, hopefully people like GraphQL. I like GraphQL, but yeah.
I'm learning to love it. Is Poseidon what is Poseidon?
Where do you see Poseidon? Or was this just
30 here? In
line
32?
Yes, there it is. So this is our, looks like it needs doc comments. This is the like hashing scheme that Mina uses. So it's like SHA-256, but instead of SHA-256, it's Poseidon. And this is just very, very efficient to do inside of zk Snark and with field elements. So it's way more efficient than SHA-256. So this is like the typical way that you hash things.
I guess the final question before you go is, do you have any recommended links or resources for people who want to start building on SnarkyJS, et cetera? Is there like a single go-to page, or is there like 5 of them? I would love to see them. Maybe you have like a slide on it or something.
Yeah. Let's see if it's in my slides properly. I need to share my screen. Yeah, I think it is. So let me pull that up. Okay. Here's the answer to your question. So the link there, the docs link, is a good kind of starting point. This is all the sort of documentation that we've written so far. I don't know if people have noticed, but it's a new project, so there might be some holes in the docs. Please open issues and we'll fill them in. There's also a bunch of blog posts that we're actively posting this week. This is actually kind of a SnarkyJS week for us. So there's a couple of other presentations going on. You can keep an eye out for those. You can join our Discord. There's a channel for zkApps developers where you can just ask things, and the developers of SnarkyJS hang out in there. And you can look at GitHub, Twitter. Yes, but I guess the docs link is a good landing page.
Oh, there's one last question in the chat. I'm sorry, but it's kind of a good generic question to end on this, I think.
Sure.
So what type of applications or category of applications do you expect people to build on?
Yes.
So is it banking application? What do you see? Like, what's the killer app use case in this case for?
Yeah, there's. I will answer this in a way that might be not well appreciated, but I see this technology as opening like an entire new way of building applications. And in the same way that like the internet opened a new way of building applications, and like who knew that YouTube was the killer use case, or like social networks, or like Zoom, like all of them are, and no one could have predicted it 50 years ago. So like I have a bunch of ideas of like what could be the thing that is the first killer product, but there's so many possibilities for what this could be. There's so many super cool things. So I'll iterate through a couple of them. Anything with privacy, and privacy, I think it's probably well appreciated in Israel. It's appreciated in many European countries, and not really America yet. So banking, like hiding financial information that you don't want to share, like maybe you want to share like specific details about certain financial information. You can connect to existing DeFi applications and enhance them with a little bit of privacy. That's sort of one category. You could do something with private data about, let's say, your health information as well. So your genome, you could say like, as asserted by the company that sequenced my genome, my DNA doesn't have this particular sequence of genes or ACTCG such that I don't have this trait. So give me a better rate on my insurance policy, something like that. So there's that kind of thing. You can use recursive zk snarks to do crazy stuff like games. So you can make a game, a multiplayer game, where the entire game sort of happens in a P2P setting and then only settles on chain after it's done. So you could have like each person take a turn, they create their next zero knowledge proof, and then they pass off that proof to the next player, and the next player does the next step and makes another proof, and you can go back and forth until the game's over. So I think games are going to be really, really interesting, and they're going to feel different on Mina than on any other blockchain. Anyway, sorry, I could keep going for like 20 minutes, but there's a lot of stuff you can do.
That sounds amazing. I really appreciate all that insight. So is there like a wallet that we can install today if we wanted to start our own ZK wallet,
Yes.
etc.? Is that also on the website there, or do we have to go to somewhere?
Everything will be in the docs. So right now, let's be really clear about what is the current state and what's coming soon, etc. So what I showed you works. You can npm install it and play with it. You can play with it with the local blockchain instance. You can play with it with proof generation turned off. You can play with it with proof generation turned on. It's a little bit slower with proof generation turned on because there's a lot of number crunching going on. The There's a couple of performance optimizations we want to do to make the proof generation part a little bit faster. We have working prototypes of connecting to the wallet and sending transactions to the chain. And if you like dig through our GitHub and different branches, you can get it to work. But it's not well documented. It's all these things. So that will come in the next week or 2 or 3. A well documented and like a new release that sort of shows that very clearly. So if you try it before then don't try. I would recommend not trying to submit to the chain yet. If you wait 1 or 2 or 3 weeks, then you'll be able to submit to testnet, play with it. This is not on mainnet yet. There is a hard fork that needs to happen. The hard fork, there will be an incentivized testnet soon that needs to happen, and then the hard fork can happen. During that incentivized testnet, you all can participate. There will be challenges to create zkApps. You will win points. The points will be converted into something that I'm not allowed to say, but use your imagination. Might be worth your time. And it'll be a great way to learn things. And then you'll be set up for when the hard fork happens that you'll be an expert on making these things and you'll be able to release things quickly. So to answer your question, the browser wallet right now, you probably shouldn't interact with it for a couple of weeks. And yeah.
Wonderful. Brandon, Kase, thank you very much for a very thorough and very, very patient session with everybody. On behalf of the Israel Web3 community of developers, I want to welcome you, and hopefully we'll see you again soon here. To everybody else who's watching, this is recorded, so you can watch this and other recordings of other meetups at israelweb3.com. And Brandon, you'll always be our guest here whenever you come in.
Thank you so much.